Okay, so here we'll look at the mathematical operation which is actually underlying of this whole problem that we're thinking about when we're working with isotopes. So let's say we have two probability density functions, the red one and the black one. Now, they do not have the same height in total. It should, of course, be 1, but this is just to give a good illustration, and contrast is always something good to have. Now, let's say we have these two probability density functions, and we would want to see what is actually happening when we are adding them. Now, to do that, we first flip one of the functions. So we'll flip, for example, the function called g, and then we would have a sliding effect. And when the peaks overlap, then we would generate a new peak. So let's see, the first peak is approaching, 1 event, 2, 3, 4. So you see that when the two delta direct peaks are going over one another, they create a new delta direct peak, of which the constant in front will be the multiplied value of the first one and the second one. And this clearly will be multiplicative if the distance is unequal. Now I can create also an equal distance, so let's do that. Let's keep it simple here. Let's see. So we have A and C, so that would be to delete this one. Yeah, okay, so you have spacing of 2, so let's make this 2. So now our first two original functions would be these two, and then you see that they have an equal spacing. And now, if we flip the function again, we remove the original one, and we let them convolve with one another, you see there will be 1, 2, 3 events. And this is because you sort of have an additive effect. Of course, we have two delta direct peaks, and 2 plus 2 is 4, it isn't 3, but you always lose 1. So it's always, let's say, if you have n plus m, then it will be m plus m minus 1. And this, of course, is far, far better than if you have m times n. And this is why I actually choose to create an equal binning. This will be explained later on. But yeah, this is actual average value will be equal to the average value if you would do the whole computation. This is rather inconvenient, and we should be able to do better. A little bit smarter approach is to use a weighted least squares. This weighted least squares allows you to indicate how often a certain element type appears inside of your protein. When you indicate how often this element will appear in your protein, you give it a higher weight, as of course the error is added. Now, you do this for each isotope, so what you basically do is you have abundance of the isotope relative to the element, and then you multiply that with the abundance of the element inside of your protein. Now, if you do this, then sometimes it will be a larger error, but the larger error will mainly be inside of the rarer protein, of the rarer isotope. So, for example, if you look at hydrogen with only one proton, or deuterium, where you have one proton and one neutron, you see that the hydrogen with one proton is better approximated than the one with one proton and one neutron. Now, this is good and well, but actually there's a way to do an even better approach. This one is rather convoluted, and I'll also make a video about how you can do this on Desmos so that you have a clear instruction on how this process actually works, and that is what we're going to look at right now. Okay, now we're going to look at the approach I created so that we can have even a better estimation of the probability density functions without losing, or rather increasing, the complexity of the algorithm. Now, on your left side, you first see a few parameters. These are integers which indicate the number of elements from a certain element type. So for example, you would have 224 hydrogen atoms inside of your protein, 190 carbon atoms, and these are just numbers I somewhat randomly have chosen. Of course, I do try to incorporate the appearance. So for example, there will not be so many sulfur inside of there, that's uncommon, but there will be a lot of hydrogen and carbon. Why I do that is because these are included for the weights, and as you will see, this is also rather handy. Okay, so first we here have a table of the atom number, so this would be the first atom number of the hydrogen, the deuterium, then the carbon 12, carbon 13, and so on. And you here have the weights, and then here you have here you have the mass, and here you have the abundance, and we simply multiply this with how often it's actually present in protein, so that we can actually get the frequency of a certain isotope, the expectance frequency of a certain isotope inside of a protein. You can neglect this one. This is just the error. So if we would have a linear regression, a weighted linear regression, which is just simply written like this. You do not need to understand this, but this is how it's written. Then you get a line like this, which is an indication. Now, of course, since it's a line with a constant slope, this is rather advantageous. And as you see, when we zoom in, you can zoom in a whole long way before you actually get to see the difference between the estimation and the actual data value. So here when we zoom in, you actually see it, but this is actually quite minor. Still, when we can do better, we should do better. So let's, for example, go to carbon 12. Let's see how it's going there. We zoom in, we zoom in, we zoom in, and only here we see the error. But still, there's an error. Now for sulfur, you do have a bit of a larger error. Let me see if I can find a larger error. Let's zoom in here. Oh, we already have a larger error. We are not even something that far. So let's see how we can do better. Okay. First, we calculate the average value of each isotope for the mass and the atom number. So this is just a simple way to write it down, and we have these certain values. So the average mass will be this, the average atom number will be this, and that we do for each different element. Now what we do is we bring all the data points to the origin, and we do this by making it such that the average value or the expectance value will be 0. And we can simply do this by subtracting the expectance mass, which is on the y-axis, and the expected atom number, which is on the x-axis. So let's see how this works. So first, we do the y-axis, and we transport all the elements to the origin. And you here can already clearly see that we treat all the elements independently, because all the elements have the different average mass and, of course, the average atom number. So now we bring them further down to the origin, and slowly but surely they're approaching the origin. How exciting. Good. So now they have a certain arrangement in which the expectance value for both the x-axis, which is the atom number, and the y-axis, which is mass, are 0. So now we do another linear regression, and then we get this line. Now this line looks very similar to the line we had before, but it is not exactly the same. Okay, so now we have a different slope value, but now we are going to do the big trick, namely that we have the same slope, but now each element will have a different offset, and this offset will introduce more flexibility in the estimation. So let us turn this one off, and we'll turn on all the estimators for different elements. And then we're going to see how this works. So first we're going to separate them. Let me speed up a little bit. We separate them on the x-axis. Yeah. So now that it's separated on the x-axis, you can see like, hey, every line is for each own element. And now we're going to separate them also in the y value. So let's do that. And now you'll see that they're almost overlapping again. Almost, but not exactly. So let's first zoom in to the hydrogen. So let's zoom in. Ooh. There you go. So you can already see that the black line is a better estimator for the first point, which is the most abundant form of the hydrogen, compared to the estimator which did it for all the elements. We can zoom in a little more to get a good overview of the difference. Now, when we zoom into the second one, let's see how that goes. How well is the estimation? So here you can already see that even though it's a better estimation, around a factor of 2, it's not like a factor 10 better. But that's logical because this line still has to have the same slope so that we get this additive effect instead of this multiplicative effect. So it has to make do with only shifting the offset to optimize, or rather minimize, the error. But minimizing the error in a weighted form, of course, means that you will have your focus on the more abundant data point, which in this case will be the hydrogen with a singular proton. So let's, for example, also look at some other examples. So here we have carbon, and as you can clearly see, carbon is the red line, and also here you have a very, very clear difference. But if you look at carbon 13, which is here, the difference is already less accurate. Now we'll just scroll through all the data points so you can get an idea. So here we are dealing with nitrogen, the first one, the most abundant one. And you can see again a better approximation. But it's not always the case that the line will give a better approximation. For example, here you see that the blue line, which is for nitrogen, actually gives a worse approximation than if we would have the approximation of all the elements which are weighted. This is just by sheer coincidence because the offset of the line and the slope are determined by all the elements, and it's just by pure chance that this line is a better approximation. But of course, since it's less abundant, it also doesn't matter as much. It's far more important that nitrogen 14, which we have here, is better approximated than the nitrogen 15 as it is far less abundant. So we'll just go through all the other elements. This is oxygen 16,